Welcome back, students. In this video section, we will take up right where we left off in part 1 to section 2.3, linear independence and bases. In this part of the video segment, or in this part 2 of section 2.3, we're going to take up with the topic of a basis. Once again, let's consider a couple of sets. So once again, consider two spanning sets for R2. We've looked at these sets before in great detail in part 1. The set containing the column vectors 1, 0 and 0, 1, and also the set containing those two vectors, 1, 0, 0, 1, but also 1, 2. We determined, or we observed, that both of the sets, they span R2. Every point in R2 can be written as a linear combination of either the first two vectors, 1, 0, and 0, 1, or the three vectors from the set that contains those two vectors plus that additional set. And remember what we're after. Remember, we are after a very specific kind of set. We are looking for a minimal spanning set for a vector space. Spanning set for a vector space. So the second set, the one that contains 1, 0, 0, 1 and the column vector 1, 2, can't possibly be it, because there exists another set that also spans R2 that has fewer vectors in it. And if you'll recall, I also posed the question then, could we possibly have a spanning set for R2 with only one element in it? The answer is no. The answer is no. So what do you expect would have to happen if we do in fact have a minimal spanning set? What do you think those vectors from the minimal spanning set should satisfy? Your hint is that the second spanning set with the three vectors forms a linearly dependent set. A linear dependent set. One vector can be written as a linear combination of the others. And we showed that. So I think you got the answer. What we would expect to have happen from our minimal spanning set is the vectors should be linearly independent. In fact, that is true. That is absolutely true. When we do in fact have that minimal spanning set, that spanning set that also happens to be linearly independent, we have something very important in linear algebra called a basis. A basis. A basis can be thought of as and this is really important. This is a nice way to think of bases. That's the plural of basis is bases. A really nice way to think about a basis is that it is a set of building blocks, a minimal set, a set of building blocks for a vector space of minimal size. Okay, every vector in R2 can be written as a linear combination of the two vectors 1, 0 and 0, 1. And those two vectors are linearly independent, so they form a basis for R2. So let's be much more formal about this. We say that the vectors v1, v2, all the way up to vn from a vector space V are a basis or form a basis, are a basis for V if both of the following, and I think you know what these things are going to be, two conditions are satisfied. One, V1, V2, all the way up to Vn. Can you guess? They're what? Linearly dependent, independent. Oof, I almost made a terrible blunder there. And two, the vectors V1, V2, all the way up to Vn, they span the vector space V. Okay, so if you have linear independent set that also spans the vector space, you have the smallest possible set of a spanning set. You have a minimal spanning set. Okay, so for example, let's let E1 equal the vector 1, 0, and E2 equal the vector, column vector, whose entries are 0 and 1. Let's let these two vectors be E1 and E2 be defined. It's easily seen that these vectors are linearly independent. So let's see that linear independence. For linear independence, we set up C1 E1 plus C2 E2 equal to the 0 vector, and then and try to determine that C1 and C2 must be 0. Okay, so it's very easy to see this. C1 times 1, 0. In fact, we already did it actually in the part 1 of the section. I'm just renaming the vectors E1 and E2. Okay, so if we perform the matrix operations, we get the column vector C1, C2 must equal 0, 0. This means C1 and C2 are both equal to 0. So that's linear independence. Spanning. We also need spanning for a basis. So for spanning, we need every vector from R2 to be a linear combination of E1 and E2. So we need for every, let me actually write that way. We need, there we go. For every vector V in R2, there exists constants C1 and C2 such that V is a linear combination of E1 and E2. V equals C1 E1 plus C2 E2. Okay, so pick an arbitrary element out of R2. Let A, B be a point in R2, or a column vector in R2. Well, let's take AB and tear it apart. We have two operations. We have addition and scalar multiplication. Definition of addition, and by the definition of scalar multiplication, that's it. I've shown that any arbitrary element of R2 can be written as a linear combination of E1 and E2. E1, E2 is called the standard basis. Standard basis for R2. There are many, many other bases for R2. Bases are not unique for a vector space. Okay, let's take a little side trip into standard bases. The common vector spaces that we've been talking about, R2 being one of them, have standard bases. and I'd like you to see them for the other common vector spaces. So the standard basis for R3 would be E1 equals 1, 0, 0. E2 equals the column vector 0, 1, 0. And E3 equals the column vector 0, 0, 1. Okay, so for Rn, the standard basis vectors are E1 equals 1, 0, dot, 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 0, and n entries there. E2 equals 0, 1, the rest are 0, etc. E sub n, 0, 0, dot, 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 1. N entries, okay, in each column vector. Okay, so very, very commonly we form a standard basis by setting one entry or one component or one coefficient equal to 1 and the rest 0. If that didn't make sense, it will very, very, very soon. Okay, so let's take a look at the standard basis for a set of matrices. The standard basis for the set of all 2 by 2 matrices with real entries is E11, which has entries all 0 except for the entry in the first row and the first column. E12, which has all zeros except for the entry in the first row and second column, etc. E second row, first column is going to have 1, zeros everywhere else. And E22 is zeros everywhere except for 1 in the entry in the second row and second column. Okay, so we can see that every element of the set of all 2 by 2 matrices with real elements of the 2 by 2 matrix A, B, C, D can be written as A0, 0, 0 plus 0, B, 0, 0 plus 0, 0, C0 plus 0, 0, 0, D, or A times 1 in the first row, first column, zeros everywhere else, etc. B, 0, 1, 0, 0 plus C, 0, 0, 1, 0 plus D, 0, 0, 0, 1. That is, every element of M 2 by 2R is A times E11 plus B times E12 plus C times E21 plus D times E22. So I have shown that these four vectors, these four matrices, span R2, or not R2, M 2 by 2R. Okay, so they're spanning. Well, okay, that's spanning. But there are two parts to a vector space. What have I not shown? Linear independence. So let's show linear independence. Linear independence. So for linear independence, we set up the vector equation C1 E11 plus C2 E12 plus C3 E21 plus C4 E22 equals the zero vector, which is the 2 by 2 zero vector, or zero matrix, and we show that those constants C1, C2, C3, and C4 have to all be equal to 0. Well, what happens when you multiply C1 times E11? You're going to get C1 in the first row in the first column, C2 times E12, C3 times E21. By doing this, we're going to pick up matrices that have one entry in one position and zeros everywhere else. So we're going to get C1, the 2 by 2 matrix, C1, C2, C3, C4. That's the sum. And on the right hand side we have the 2 by 2 zero matrix. Two matrices are equal if and only if the corresponding entries are equal to 0. This is the first thing we started out with matrices. Matrix arithmetic. Something our author skipped was equality of matrices, kind of important. So the set is linearly independent. Okay, so E1, E11, E12, E21, and E22 are linearly independent. Okay, let's take a look at another common vector space for us. These are vector spaces that we're going to be seeing a lot of this semester. Okay, suppose I want the standard basis for P sub n, the set of all polynomials of degree less than or equal to n. Standard basis 1, x squared, x cubed, etc., all the way up to x to the n. Okay, spanning. That means I want to show that every element of Pn can be written as a linear combination of these vectors. Pick something out of Pn. Let P be in Pn. Okay. What does then P look like? P has to look like A0 times 1 plus A1x plus A2x squared plus ... all the way up to ANX to the n. Why? Because that is what an element of Pn looks like. Pn is the set of all polynomials of degree less than or equal to n. There it is. There's the form of a polynomial of degree less than or equal to n. The constants a0 through an are just scalars. Some of them can be equal to 0. N could be a sub n could be 0, in which case we have an n minus first degree polynomial, etc., etc., etc. So spanning. I have shown that every element of P sub n is a linear combination of the vectors 1, x squared, all the way up to x to the n. Okay, I've shown that every vector is some linear combination. Every vector from P sub n is some linear combination of those n vectors. Okay, so linear independence. I'll start the abbreviation thing. Set up the equation C1 V1 plus C2 V2 plus C3 V3. Let's do our constants starting at 0. Yeah, I think just to make it simpler on us, the constants don't have to start with 1. They just have to be constants. So here's our C1 V1 is really C sub 0 times 1 plus C2, well, we're going to call it C1 x plus, just so we can have the subscript correspond with the exponent, C2 x squared plus ... plus Cn x to the n equals the 0 vector in p sub n is the polynomial y equals 0, or p of x equals 0. This polynomial equation has to hold for all x. We're not looking for the solution to this equation. That's a different kind of problem. This equation is supposed to hold true for all x. The only way this could possibly hold for all x would be if c sub 0 equals 0, c sub 1 equals 0, c sub 2 equals 0, etc., etc., c sub n equals 0. Okay, so done. Okay, so the set is linearly independent. 1x, x squared, dot, 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 x to the n is linearly independent. I have two things happening. I have that fundamental set, that standard basis spanning p sub n. Everything in p sub n is a linear combination of those, and they are linearly independent. Okay, so they are a basis. In fact, they're called the standard basis. Okay, more examples. Not every basis is the standard basis. Not every basis is the standard basis. Okay, so here's our example. Determine whether the set v1 equals 2, negative 1 and v2 equals 3, 2 form a basis for R2. Okay, that is what's going on in the background. What is a basis? We're saying that we want to determine whether every point in the xy plane, expressed as a column vector, of course, can be written as some combination of these two vectors. Okay, well, let's check linear independence. Okay, so let's let c1 v1 plus c2 v2 equal the 0 vector in R2, and determine the nature of the constants c1 and c2. Hopefully they're both 0. If they're both 0, we have linear independence. So set c1 times 2, negative 1 plus c2 times 3, 2. Set that equal to the 0 vector in our vector space. So this says that we have a system of equations. Here we go again with the systems of equations. This is very common in linear algebra. Systems of equations are extremely common. Okay, now we're not looking for the solution. We're just supposed to, actually, no, that's false. We are looking for the solution. We're supposed to determine that the only constants are 0 or otherwise. So sorry about that. That was a little flub. Okay, we have a 2 by 2 system. We have a system of 2 equations and 2 unknowns. So we're going to connect the solution with the determinant of the coefficients. The determinant of the coefficients is 4 minus negative 3, and that's 7, which is not 0. If the determinant of the coefficients of a square system is not 0, that implies we have a unique solution. But the system is a homogeneous system with the trivial solution. So that implies that the only solution is that same trivial solution. C1 equals 0 and C2 equals 0. And that's it. If we didn't get that uniqueness part, then we would have work to do. The fact that we have a unique solution, and combined with the fact that every homogeneous system has the trivial solution where the variables are all equal to 0, says that the only value for the variables are 0, and that is precisely the definition of linear independence. That implies V1 and V2 are linearly independent. Spanning. We want to show that, or determine whether, every element of R2 can be written as a linear combination of these two vectors. So pick something out of R2. Let V equal AB be an element of R2. I'm not specifying which one, just an arbitrary element. I need V equal to C1 V1 plus C2 V2. It would be nice if that happened. Okay, that is, we need AB to equal C1 times the first vector plus C2 times the second vector. We'll assume that we can take some liberties here. Assume that we can do that. Assume that we can take AB and write it as C1 times 2 negative 1 plus C2 times the other vector, 3, 2. It may not be possible to do that. Okay, but assume that we can. That's going to translate into another system of equations with exactly the same, now listen carefully to this, exactly the same coefficient matrix as we got in the system that helped us determine linear independence. The only difference is we have AB as the constant terms and not 0, 0. That's very important here. It's going to be much more important in the next section, that we get the same system. The determinant of the coefficient is still 7. It doesn't change, which is not 0. So again, that implies that there exists, and I'm putting in parentheses unique, because it's not important in this part of the problem. For linear independence, the fact that the solution was unique was essential. Here, there exists a unique, but unique is not important. There exists a solution. Okay, that implies there exists, maybe more than one, but there exists C1 and C2 such that V is C1 V1 plus C2 V2. Remember, C1 and C2 were those coefficients we were assuming existed, and we were going to try to prove that in fact they did exist. We just did that. If this system had no solution, then our assumption that we could write AB as a linear combination of our vectors would have been false, and we would have had we would not have spanning. We would not have spanning. Okay, so both of these things. Oops, let me write it different. Let me write it the other way around. Oops. I'm trying to get my eraser out of here. So, linear independence, and spanning implies that we have a basis, so that the vectors V1 and V2 form a basis for R2. Now again, notice the similarity between what we had to do with linear independence and with spanning. They both of those things, both of those ideas were hinged on the determinant of the coefficients of two different systems that had the same coefficient matrix. Okay, that's gonna mean something in the next section. There's a connection between linear independence and spanning. It would be nice if we only had to show one of those two things. Under some circumstances you'll see up in the next section, we will only have to determine one of those two things. But there's another thing that'll have to have happen, so let's not jump the gun. Okay. Let's look at another example. Example. Ooh, suddenly I'm still in red. Okay, so example. Determine whether the vectors x cubed plus x squared. We've seen these vectors. X cubed plus x squared plus x. What was the third one? X plus 1 and 1 form a basis for P sub 4. Set of all polynomials of P sub 4. P sub 3, sorry. P sub 3. Set of all polynomials of degree less than or equal to 3. Okay. Well, instead of calling these vectors v1, v2, v3, and v4, I'm going to use symbols that are common for polynomials. So let's call p1, small p1 equal to x cubed plus x squared, small p2 x squared plus x, small p3 x plus 1, small p4. Okay, so it's like p1 of x, p2 of x, p3 of x, p4 of x. Okay, so we're going to use the symbols that are common for polynomials. Linear independence. We already did it. We did this in, I think it was part 1 of this video segment. In this section, we did this in a previous example. We showed that these 4 vectors were linearly independent. So spanning. Okay. So pick something out of P3. So let's let P of x be an element of P3. Okay. Well, we need, what do we need for spanning? We need P of x equals, let's see, what do we want to use for variables? We need P of x equals C1 P1 plus C2 P2 plus C3 P3 plus C4 P4. This is what we need to have happen. Okay, let's see if we can get that to happen. So P of x is in P3. So that means P of x is a polynomial of degree less than or equal to 3. So P of x must be of the form ax cubed plus bx squared plus cx plus d. This is a given. P of x comes from P3, so it has to be a third degree, a second degree, a first degree, or a constant polynomial. And there's the general form. So what we do is we set that polynomial, that general polynomial from P3 equal to C1 P1 plus C2 P2, etc., etc., etc. So set ax cubed plus bx squared plus cx plus d equal to C1 P1 plus C2 P2 plus C3 P3 plus C4 P4, and see if we can find constants C1, C2, C3, and C4 that will make that true. Okay, well, that equation is going to get a little long, so it's x cubed plus ax cubed plus bx squared plus cx plus d equals C1 times P1 x cubed plus x squared plus C2 times P2, I already forgot what P2 was, x squared plus x plus C3 times P3 x plus 1. Let me make that a little neater than that. That's not that much neater. Plus C4 times P4. And then determine the nature of the constants. Gather all the powers on the right you're going to get C3, oops, not C3, C1. You're going to get C1 must equal the coefficient of x cubed on the left. You're going to get C1 plus C2, very similar system that we got when we showed linear independence on that, equals B. You're going to get C2 plus C3, jumping a little too fast. C3 equals C. You're going to get C2 plus C4 equals D. Just making sure I believe that. No. You're going to get C3 plus C4 equals D. Much better. Okay, so this is a system of 4 equations and 4 unknowns. So the solution is going to be connected to the value of the determinant of the coefficients. 0, 0, 1, 1, and 0, 0, 0, 1. This determinant is still 1, just like it was before when we were doing linear independence. The 1 is not 0. Now, that implies that there exists, the unimportant part is a unique. The important part is a solution to the system. There exists a unique solution. Remember, that's what we're going to be using over and over and over again with these square systems. There exists a unique solution if and only if the determinant is not 0. The determinant is not 0, so we have a solution. Happens to be unique. We don't need that much out of that. But that says there exists a C1, C2, C3, and C4 such that P of X equals C1 P1 plus C2 P2 plus C3 P3 plus C4 P4. That's exactly what we needed for spanning. Therefore, P1, P2, P3, and P4 form a basis. Well, I should say span first. Therefore, span P3. Therefore, since we have linear independence, these vectors form a basis for P3. Okay. Okay, so what I'd like to do next is address the another powerful property of the basis vectors. That has to do with the uniqueness of representation of elements from a vector space using basis vectors. What I'm basically saying is that if you have a basis for a vector space, there's only one way to write each vector in that vector space as a linear combination of those basis vectors. There's only one way to write a point in R2 as a linear combination of E1 and E2. If you really think about it, that's pretty obvious. There's only one way. Let me see if I can squeeze this in blue. There's only one way to write the point 1, 3 in terms of the basis vectors 1, 0 and 0, 1. There's no other way using these two vectors, 1, 0 and 0, 1, the standard basis vectors, of writing this. The only constants that could be multiples of our basis vectors are 1 and 3. The only constants that could be used to form this point 1, 3. Okay, so this theorem is basically saying that in general, the theorem is an if and only if theorem, just like one of our previous theorems, but I've broken it down into two parts, and I'm going to prove one way. Okay, the theorem says this. At least part 1 says this. Let's start with v1 to vn vectors in a vector space. Part 1. If those n vectors form a basis for V, then each vector in V is uniquely That means there's only one. It's uniquely expressible as a linear combination of the vectors in v1 to vn. Part 2 is the converse, or the reverse, or however you want to think about that. Part 2 says, if each vector in a vector space is uniquely expressible as a linear combination of those n vectors, then those n vectors form a basis. I'm going to prove part 1. Your author proves part 1 and 2 and does a decent job at it. You should read through and understand part 2. Okay, so proof. Part 1. I like blue. We'll stay with blue. Part 1 says we're starting with n vectors that form a vector space. So let's let v1, v2, all the way up to vn form a basis. Form a basis for v, a vector space. Okay. Now I want to show that every vector in V is uniquely expressible as a linear combination of these vectors. That means I want to show that every element in the vector space can be written in terms of these basis vectors only one way. So we're going to use a common method of proof for showing uniqueness. We're going to assume that there are two representations and then show that those two things must be equal. So let's start with something in the vector space. Let's pick something out of the vector space. Let V be in the vector space. So what justifies me being able to do that? What justifies me being able to pluck something out? Because vector spaces are non-empty, that's why. Okay, so we need to be able to justify every step. Let's assume that we have two different representations from this basis. Let's assume that V equals some C1 V1 plus C2 V2 plus all the way up to Cn Vn. And let's assume that we have a second representation. V equals D1 V1 plus D2 V2 plus all the way up to Dn Vn. My goal is to show that all the C's should equal all the D's. Okay. Well, if I have these two separate representations of V, then when I subtract them, I should get 0. So I should get 0 when I take V and add the opposite of V, which is what we define as V minus V. Well, V plus the opposite of V, if we use those 8 properties of the vector space and gather all the constants together, we're going to get C1 minus D1 V1 plus C2 minus D2 V2 plus all the way up to Cn minus Dn quantity times Vn. Okay. I'm going to get that whole right-hand side equals 0 with the C1 minus D1 V1, C1, etc., etc., etc. Okay. I claim that each of those coefficients, C1 minus D1, C2 minus D2, all the way up to Cn minus Dn, I claim that those should all equal 0. Why? 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 Why should the coefficients be equal to 0? Because I'm assuming that V1 to Vn form a basis. Since V1 to Vn form a basis, they are linearly independent and they span the base, the vector space. Back to the first thing, they are linearly independent. So the coefficients, when I set up any equation with coefficients of V1 and V2, any equation that adds up multiples of V1 to Vn equaling 0, the coefficients should be 0, since V1, Vn are linearly independent. It's over. So these are just scalars. C1 minus D1 is a scalar C1 minus scalar D1. So add D1 to both sides. C1 should equal D1. C2 should equal D2. Cn all the way up to Cn should equal Dn. It's over. I assumed that there were two separate representations of V, a typical element from the vector space, using the basis vectors. I've shown that all of the coefficients from one should equal all the coefficients from the other representation. That is, there's only one representation. That implies the representation is unique. Representation is unique. I'm leaving the part 2 for you to read. It's not difficult at all, but I'm leaving it for you to read from your textbook. Okay. Okay. Okay, now we're getting close to the end of the section, but we have another little subtopic to talk about. This isn't a difficult one. This one's pretty simple, straightforward. Okay, we will often use lowercase Greek letters to denote different bases. This is no big deal, by the way. So, for example, if, and I think I'm going to get away from blue, if alpha, the Greek letter alpha, is, let's say, the basis for V, a vector space, a vector space, and let's say V is an element of the vector space, capital V, then I never identified the basis. I'm going to start that sentence over again. So if alpha is the basis, let's say V1 to Vn, sorry about that, folks, for V, let's say the vector space, and V is an element of the vector space V, then V equals C1 V1 plus C2 V2 plus dot 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 plus Cn Vn for some scalars C1, C2 all the way up to Cn. I haven't said anything different, anything new here. I've just identified the basis by the small Greek letter alpha. That's all I've done here. Okay, the constants C1 to Cn that we see in this vector representation have a very special name. Okay, the constants, the scalars, the constants C1, C2, all the way up to Cn are called the coordinates. This is going to be very important in chapter 5 coming up in about a month and a half or so. They're called the coordinates. The coordinates of V relative to the basis alpha. Okay. The column vector, let's write that column vector here. The column vector made up of those constants, C1, C2, all the way up to Cn, is denoted by, in brackets, V sub alpha. That column vector is called the coordinate vector. The coordinate vector. Vector of V relative to the basis alpha. Okay, so the numbers C1 to up to Cn that make up that are used to make up, using the basis, the vector V, those constants, those are called the coordinates of the vector v relative to the basis we're in, basis alpha. When you form the column vector with those coordinates, you have something called the coordinate vector of v with respect to the basis alpha. It may seem that like I'm presenting you with something complicated, but I'm not. I'm going to finish this lecture with a few examples about coordinate vectors or regarding coordinate vectors. So for this example, suppose alpha is the standard basis E1 1 0 E2 0 1 for R2. So suppose alpha is the standard basis which contains E1 and E2 for 2 space R2. Okay. So if V is an element of R2, we've done this basically before, then V equals some column vector AB, and that will equal A times E1 plus B times E2. Okay, so the coordinate vector of V relative to the basis alpha is just A, B. We pick off the multiples of E1 and E2 that are used to construct the vector V. In this case, the coordinate vector and the vector itself turn out to be the same thing, but it's not always the case. Okay, the coordinates are just the entries of the column vector of the vector related to the standard basis. Okay, so let's take a look at another example if that didn't make sense. For example, for M, the set of all 2x2 matrices with real entries, V equals A, B, C, D. Elements from the set of all 2x2 matrices with real entries look like A, B, C, D. And we determined that representation looks like, for using the standard basis vectors, A times E11 plus B times E12 plus C times E13, if you C21 plus D times E22. If that doesn't ring a bell, you should look back at that portion of the videos for this section that had us do that. I think it was part 1. So in this case, the coordinate vector of V relative to alpha is the column vector A, B, C, D. Okay, and I realized as soon as I did that, I didn't identify what the basis was. So where, even though I was using them, alpha is the standard basis. E11, E21, oops, E12 rather. E21's in there, also E22. So in this case, the coordinate vector for a 2x2 matrix is a column vector. In fact, the coordinate vector doesn't have to look anything like the actual vectors in the vector space. In this case, the coordinate vector is a column vector. The vectors in the vector space are 2x2 matrices. Okay, another one. So, example. For Pn, and of course using the standard basis for Pn, and I'll identify it at the end as like, just at least I'm being consistent with my last example. For P sub n, P of x, an element from P sub n, is equal to C1 times 1 plus C2 times x plus C3 times the third basis vector, x squared. And I'm doing it again. I think I'm going to backtrack on the coefficients. It's just a little easier on the eyes to have the subscripts match up the exponents. So for p sub n, any p of x in p sub n can be written as a linear combination, we've seen this several times, of the basis vectors 1, x squared, all the way up to x to the n. So the coordinate vectors of, let's say, p with respect to alpha looks like C0, C1, all the way up to Cn. So the coordinate vectors are always column vectors. They're always column vectors, even though the vectors in the vector space may not have anything to do with column vectors. P sub n is polynomial, set of polynomials. Okay, so again, this is where alpha is the standard basis. 1 x squared all the way up to x to the n for p sub n. Okay, so for standard bases, it's extremely easy to identify the coordinate vector or the coordinates if you don't want to write them in vector form. For non-standard bases, finding coordinates is tougher. Okay, for non-standard bases, finding coordinates is tougher. So what I'd like to do is one example to end our section on finding the coordinate vectors of a particular vector in a vector space relative to some non-standard bases. Okay, so for example, find the coordinate vector. Find the coordinate vector of the vector v equals, let's say, we want to let v equal, what vector space do we want to be in? We'll be in P3. So x cubed minus 2x squared plus 3x plus 5. So maybe I'll use, instead of v, I'll use p. Find the coordinate vectors of the vector p equals that polynomial relative to the basis beta, let's say, for P3, consisting of, you guessed it, x cubed plus x squared plus x plus 1, and 1. Okay, so I'm looking for the coordinate vector, which means I'm looking for the coefficients of the basis vectors used to express the vector p in terms of the basis vectors. Okay, so I need to take our vector p, which is x cubed minus 2x squared plus 3x plus 5, the ugliest looking 3 today. Here we are. And I need to set that equal to c1 times x cubed plus x squared plus c2 times x squared plus x plus c3 times x plus 1 plus c4 times 1. Okay. Once again, this amounts to the system of equations with 3 equations and 3 unknowns. C1, the coefficient of x cubed, needs to equal 1. C1 plus C2 has to equal the coefficient of x squared, -2. C2 plus C3 needs to equal 3. And finally, C3 plus C4 needs to equal 5. Okay. Now, we're not showing linear independence or spanning. We are actually after the constants. We're not showing spanning here. We're after the constants, C1 through C4. So we need to solve this system. We have the Gauss-Jordan elimination method, which will do just nicely on this. I'm going to use Gauss-Jordan elimination. 0, 0, 0, 1. Here's the augmented matrix. I'm going to save you having to look at any of the row reducing. So I'm going to compute the reduced row echelon form, and that will give us 1, 0, 0, 0, 0, 1, 0, 0, column wise 0, 0, 1, 0, 0, 0, 0, 1, with final column 1, -3, 6, and -1. Okay. So it tells us C1 equals 1, C2 equals -3, C3 equals 6, and C4 equals -1. Okay, so we don't want to get lost in what we've just done. We're taking a polynomial from P3, a specific one, and we're trying to write it as a linear combination of a set of basis vectors. The same set of basis vectors has been following us through this darn lecture. So I have done it. I found what the constants should be. So my polynomial x cubed minus 2x squared, I forgot what the polynomial was, plus 3x plus 5, is equal to C1, 1, times the first basis vector, x cubed plus x squared. C2 is -3, so -3 times the next basis vector, x squared plus x. C3 is 6, so plus 6 times the basis vector, x plus 1. C4 is -1, so -1 times the basis vector p of x equals the polynomial 1. That's what I've just shown. You're guaranteed that if you multiply all that stuff out on the right, that representation will equal x cubed minus 2x squared plus 3x plus 5, our vector. Okay. Okay, so to end the video segment, we were looking for, don't need to be in red here, the coordinates vector of P with respect to the basis beta is simply 1, -3, the column vector, 1, -3, 6, and -1. Okay, we're not going to see too much usage of the column vector, the coordinate vectors rather, until chapter 5, but they do come back in a big way in chapter 5, in particular in section 5.3. So this ends part 2 of the section 2.3. When you have a chance, go ahead and dig into the homework for this section. It's kind of a long assignment, and as usual, I am looking forward to talking with you all again soon.